Hi, good morning, everyone. So today we will start Verilog. Okay. So till now in the digital electronics, we discussed about the logic gates. Let's say if you are designing a flip-flop, let's say if you are designing a flip-flop. So what and all requires? So it means you need NAND gates connected in a different way. Okay. Okay. So inside a flip-flop, you require an AND gates. The way they connected an AND gate, and if there is a clock, you need an extra control. That is transferred into the NAND gates, the flip-flop. Okay. Then how the NAND gate is designed? We know that CMOS logic, right? How the NAND gates are designed. Drain source connections. So you are from mapping from flip-flop to NAND gates and gates to analog. So this kind of mapping is required to design any circuits. But it is not easy to design a CMOS gates for every time you're writing a code. Let's say you're writing a code for a bigger finite state machine. Let's say you detected 10110 pattern. In the state machine, you have a flops and you have a combinational logic and you have a flops. And to design all these kind of things by using this raw approach is very difficult, right? Because each and every flip-flop has 4 number of NAND gates, and combination also has some AND or XOR, XNOR every gate. So all number of logic gates will be present. But to design all these logic gates every time with this CMOS logic, it will be something very difficult. Okay, up to digital part we can design up to gate level, like NAND gates or gates we can design. But designing each and every gate and mapping them to analog by manually, it is a very hectic work. So that is why we introduced a tool, or else we can say it is in a language which will convert your intentional gates, logic gates, let's say NAND, flop, XOR, XOR, all the logics into this analog format internally. So you need not to take care of anything related to analog. So in the Verilog, you can only need to take care of digital part. So let's say if I want to design an AND gate, so you will have some keyword for the AND gate, or else you have the symbol. So if you use this word AND, okay, so then this Verilog tool will take in care. Okay, AND means AND gate, so it will take the CMOS circuit and it will give the output based on the symbol you are giving. Let's say you are using OR gate. Okay, so then it will map internally. Internally, Verilog language will take care of this mapping from this digital part to analog part. Okay, so that is the required need of the Verilog. Okay, so let's say if you're writing and A and B, so then tool understands this and means and gate. Okay, so the AND gate, how it is performs, everything will be taken care by the tool. So how the AND gate is designed with the CMOS. So all this mapping will be taken care by the tool. So you only need to write this one in the language. So A and B. So AND means it will take care, it will consider it as an AND gate. So AND gate, how it is designed, how it is producing output, everything will be taken care by the tool. So before designing anything, you need to define the functionality. Let's say if you want to design a flip-flop, you should know the functionality of the flip-flop. Like let's say, let's say you have the flip-flop D, Q, and you have clock, and you have reset. So you need to decide the functionality of this flip-flop. Okay, let's say the flip-flop, if reset equal to 1, then Q is directly becomes 0, irrespective of the clock, D, anything. So that is what my requirement. Okay, and if reset equal to 0 and clock is the positive edge, then what we have to do, Q equal to D. This is the functionality of the D flip-flop. Okay, so whenever the positive edge of the clock is received, at the time reset, if the reset is 0, and then it will be Q equal to D. So that is what my intention. Yeah. So you understand the importance of the Verilog now. So now we will discuss about this language. What are the syntaxes, keywords, data types, everything. Okay. So first thing is how to write the comments in the this hardware description language. Let's say you are writing a code in a Verilog format. The format, the file extension you have to create with .v. Let's say if I want to write a code for state machine, so I can create a file state machine.v. So .v means your Unix will understand it is a Verilog format. Okay, so all the files, like let's say in a C you are giving with some extension, and in Unix you'll give with some extension, something. Similarly with all the Verilog files, you have to give in with the extension .v. So inside the file, these comments are like similar to the C language. So if you want to write a comments in a single line, let's say if I write a code A and B, C equal to A and B, and if I want to write a comment something at the end, after this I have to write a comments. So this double slash means you can write the comment up to this line only. Okay, this double slash is valid until and unless \n. Okay, if you enter into the next line, then you have to write a code. So this comment is no longer valid. Okay, if you want to write a single line, you have to use the double slash if you want to write a single line comment. Let's say if I want to write multiple line comments, let's say if I want to write 4 lines, then I have to give something like this: slash star and star slash at the end, start and end. Then the tool considers whatever all the lines present in between these two keywords, okay, will be considered as a comments, and it will not execute while performing the operation. Okay, so these are the two type of giving comments. And so here are some basic operators. So remember one thing, the knowledge I am giving in the Verilog is only is you can understand the code which is written by someone. Okay, so if you want to write your own code, then you require some expertise, and this Verilog itself will take 2 to 3 months. Okay, so I'll, because our main aim is DFT, right? So I'm just giving the introduction to Verilog and some keywords and some data types so that you can understand the code which is written by someone. Okay, so that is the knowledge is more than enough for the DFT engineer. Okay, so let's discuss about the operators in Verilog. Okay, so operators are these operators are mainly divided into 3 categories. One is unary operators. Second is binary operators. Third is conditional operators. Okay, so unary operators means, so if you perform any operation, not and whatever the operation you are performing, if you are performing only on the single variable, then we can say it is as a unary operator. Okay, let's say if I write a is equal to inversion of b. So what is the operation you are performing? You are negating the value of b. Okay, so the operation is performing only on the variable b. Okay, that is why we can call it as a unary operator. Okay, so this is the inversion. This is the gate we are using for a NOT, the symbol which we use it for a NOT. Okay, so this we can say unary operator. Okay, and binary operators. So binary operators in the sense, let's say if I perform a equal to b and c. Okay, then so the AND operation is performing in between more than one variables. See, b and c. So the operation, whatever the operation, whether it is AND or XOR, whatever the operation you are performing, if you are performing on the 2 variables, more than more than one variable, then we can say it is a binary operator. Okay, so if the operation is performing on the single variable, then it is a unary operator. If the operation is performing on more than one variable, then it is a binary operator. Okay, conditional operator means, so the operation we needs to perform depends on some condition. Let's say a is equal to b, question mark. If I write question mark, then we can say it is a conditional operator. Okay, so question mark in the sense, if b is equal to 1, then whatever the statement I written after the question mark, first statement, then this will execute. Okay, let's say C, here it is D. If I write something like this, so then normally if I write A is equal to C, so C is assigned to A. If I write C, A is equal to D, D is assigned to C. But I need condition. Then what I am writing, A is equal to B question mark C colon D. What it is meaning? So B is equal to 1. So whatever the value of C will be replaced by this entire statement. Okay, so this entire statement will be replaced with a C. So if B is equal to 0, then this entire statement is replaced with a second one. So it means if B is equal to 0, then A is equal to C operation will be performed. If B is equal to if B is equal to 1, then this operation will perform. If B is equal to 0, then this operation is performed. You need not to explicitly mention, like if you can use if conditions as well. If B is equal to 1, something like that. But shortcut is now very long. In C language, you are getting the if and while else loop, right? In C language, you can write if A is equal to 1, then you can write B is equal to 1, then you can write A equal to C. Else, you can write A is equal to C. This is the way to write in C language, as I remember, right? So, but this is the shortcut in a Verilog. A equal to question mark C colon D. So it is more likely to mux operation, right? So this is the way to write a Verilog syntax for the mux. And you know A and B, or you know not, this is the not operation, and this is the operation for mux. These are the basic operations. Okay. So if you want to produce NAND NOR, then you can simply use this and overall if you apply this one, right, tilt, so this one, so it will become NAND. So if you apply same thing A or B, then it will become same. Okay, so NAND and NOR. So with this you understand, right, what are the basic keywords which is used in Verilog to represent each and every combinational gate. Okay, so this is for AND, this is for OR, this is for NOT, and this question mark is used for a mux. So let's see what is for XOR. XOR, the symbol is this cap. So let's say if I write C is equal to A cap B, then it means A XOR with B. This is the symbol for XOR gate. So if you want to produce XNOR, then simply use this one. That's it. So these are all the symbols which are used in a Verilog to represent each and every combinational gate. Okay, there is no direct symbols to represent half adders, full adders. You can use arithmetical operators. Plus, these you might all aware, right? Plus, minus, star is a multiplication. So these I don't want to explain it again, because if C is equal to A plus B, so it is representing arithmetic addition. So this is differ from C is equal to A single bar B. Okay, so this is R. This is arithmetic addition. Got it? So these are two are different. Similarly, and also. So C is equal to, if I write A star B, it means it will multiply. Okay, if I given C is equal to A and B, it will be a binary AND. We can say AND gate, OR gate, NOT gate. This is used for mux. This is XOR. Okay, these are some basic operators and keywords which are representing. So not keywords, these are the operators which are representing each and every combinational gate in the digital electronics. But for flop, there is no direct symbol. Like if you want to design a flop, you cannot directly use some symbol to represent the flip-flop. You need to write some code which will generate the flip-flop in the Verilog. So the remaining AND or all the basic operations and universal operations, you will have direct symbols. You can directly use them. Okay. And so next thing is how to give the values, direct values in the Verilog. So in C language, if you want to assign, let's say you're declaring a variable C is equal to 10, something you can directly define something like this in a C language. In Verilog, you need to declare not directly something like this. You have a multiple options because we have more number of number systems, right? We have binary number system, we have decimal number system, we have octal number system, we have hexadecimal number system. Usually these four are the universal number system which is accepted by the industry. So if you are defining a number, then you should tell the tool which number system you are referring to. Okay, so let's say if I given just 16 directly, by default, Verilog will understand all the numbers. By default, it is considering as a decimal numbers. If you are not giving without any constraint or without any extra keyword, it will consider as a decimal number. If you want to give hexadecimal number, then what is the notation? Hexadecimal number means 0x you have to give. Whatever the number you are writing after that, it will consider it as a hexadecimal. So let's say if I want to define declare a variable like C is equal to 0x B. So now the C is a variable with hexadecimal value of B. Understood the notation? C is equal to 0. So that is the notation. And if I directly define something like this, right? So the tool will allocate some memory to the variable to store this value. So this is the concept from the C language. Let's say if I define a variable C, C is equal to, let's say if I'm writing 16. So if I'm not giving anything before that 16, it will consider as a decimal, right? And to store the value of C, it will allocate 32 bits in a binary to store the value in memory, because each and every variable you are defining in the program, so there is some memory which is allocated for each and every variable. What is that? Have a case where B equal to 8, then we want to A equal to B, then else we want to use A equal to D, then we can use operator equal to B, and then else we want to use A equal to I didn't get that. So if there is B equal to 8, then we want A equal to B.
Can you hear me?
Okay. And else we want to use A equal to D. Then why C come into the question mark? Because there is nowhere is present, right? C. I think. First A equal to C. No, this is the assignment which is only for 1-bit comparison. Let's say if you are giving 8 in the sense, what it is meaning in the binary, how many bits you are representing, that is important. Because if you are giving a question mark, you should be able to, you should use only single bit. This is just a binary comparison, not with the number, full number comparison. Okay, so the B means only single bit if it is 1 or 0, that's it. And if you give a multiple bits, right, let's say if you want to operate in such a way, so you have to declare B with the some port declaration 3:0, something like that. Otherwise it is considering as B as only single bit. Okay, if you are declaring B as the input or output, that we will discuss later, whatever input and output I'll explain. So if you declare input as B, then it will be a 1-bit, then this will be valid. Okay, if you want to give B equal to 8, right, 8 means 1 1 1. So you need to declare B in such a way that 2:0. If you want to give only up to number 8. So 8 means you require 3:0. Sorry. Okay. So 8 number is how you are representing 1,000. If you use that question mark B, then tool is expecting all the bits of the B should be equal to 1. Then only it will go to C. Otherwise, D will assign. Understood? So if you are giving multi-bit number, let's say B is a single bit, then this is valid. If the B is equal to 8, then you have to declare in such a way that so B question mark C equal to D. So then you cannot give B equal to 8, B equal to 7, you cannot get it. Only you can get if B equal to 1 1 1 1. So only in the single case, the value of C is assigned to A. So for all the remaining cases, D is assigned to A. Okay. If you are giving multi-bit input in place of single bit, then the tool is considering the bits as a single bit. Okay. So B, it is expecting all ones if you're giving and the question mark.
Okay. Can you hear me?
Sorry.
Can you hear me?
Yes.
Okay. So basically, so each time when we have A is equal to B question mark C equal to D, the B has to be 1. In order to get A is equal to C, B has to be 1, no matter what.
For your question, the solution is the case statement. So with this question mark approach, you cannot get required operation. You have to use the case statements after B. Case statements, you can write any values. So you can declare B as a multiple inputs, and you can write a code for B equal to case 08, something like that. So I'll explain when we enter into the case statement explanation.
But this question mark is for the mux also, right?
Sorry?
This question mark, we use it for the mux.
You can type, your voice is not clear.
Oh.
If you want to get that specific operation which you pasted in the chart, we require case statements with the mux. Especially you cannot represent. No, you can use the case statement. Okay, but in the conversion, you cannot decide whether mux will be instantiated or another gates will be instantiated. That is completely tool will decide. Okay, you just have to write your requirement. That's it. If you want to, if you are writing with the question mark, if it is a single bit, then it might have mapped into a mux. Okay, so if you write a case statement, even if you write a case statement, still there is a chance of tool can convert into mux or else gates. Even though if you are writing B question mark C something like that, right? It is not guaranteed that it will be directly converted into the mux operation. It might reduce the operation, it reduce the logic, and it might represent the same with the gates also. But the operation, whatever you are expecting, it will replicate in the gates. That's what. So there is no specific direction that tool should use only this mux, only these AND gates, only these NOT gates, only these XOR gates. So you have to fill your what we can say, you have to fill your requirements with the symbols. So whatever the gates it should represent, that tool will decide. Okay, you have to use your best keywords to represent your operation. So from the keywords to gate mapping, tool will take care. Understood? Yeah. So where we are, so we come back to that variable definition. Let's say if I define a variable. Okay, let's say if I assign C is equal to 16. So then what tool will do? It will allocate 32-bit memory, 32-bit binary memory to the variable C, and it will store the value of 16 in form of 32 binary bits. Let's say 0, it means 0, 0, 0, 0, 0, 0, 0, and the last 1, 4 zeros. This is the way 31, 0. This is the way tool is storing the value of any variable. Okay, so if I don't want these 32 bits to utilize in the memory, okay, so let's say if I'm using a variable which is having only 2 bits, let's say C is just I want to use the 2 bits of the memory. So then you have to write 2 tick. Okay, so this is the representation of these 2 single hyphen. Okay, so this is the representation, means tool will use only 2 bits of the memory to store the value of C. That's it. Okay, so if I write C is equal to, let's say, 5 tick, it means it will not use the 32-bit memory, 32-bit location in the memory. So it will use only 5 bits of the memory wherever it is present. It is just using only 5 bits to store the value of C. And whatever the value you are giving, that is up to you. And you need to specify which format you are giving. See, let's say if you are writing the number, let's say if I write 8. So you need to give which format you are writing. So whether you are writing decimal, binary, hexadecimal, octal, you need to represent before that number. Let's say C is equal to 5 tick B 00110. Got it? So this 5 tick represents 5 bits of the memory is allocated to the variable C. This B represent you are writing the next number in a binary format. Okay, so let's say if I write C is equal to 7 tick O, what I can write 22. Okay, so it will so the tool will allocate 7 bits of memory to represent 22 octal number 22. Okay, it will convert in this octal number into binary format. Okay, let's say we can say octal number means 010 Okay, so these 6 bits will be stored in the 7 bits which is allocated so the remaining bit is 010. This is how it will store. Okay, so whatever the format you are giving here, octal, decimal, hexadecimal, binary, internally tool will convert everything into binary format, because we already discussed in digital systems the only number system is binary number system. For user convenient, we are defining the these remaining number system, decimal, octal, hexadecimal. But the only number system which tool understands for all its operations is binary. So whatever the number system you are giving, it will internally convert into binary and performs all operations, and then again convert into the required number systems, and it will display in the output. Okay, so this is what internally will happen in the digital electronics. I mean, digital tools, all we can say, all digital tools. Let's say if I write D is equal to 16 tick hexadecimal value of 32AB. So it means 16 bits of the memory is allocated to the variable D. So it means 16. Okay. So now these all hexadecimal numbers are converted into binary and they will store. Okay. So now if you see, three means 0011. 2 means 0010. So I'm directly converting because 16 is 2 power 4. Binary is 2 power 1. 16 is 2 power 4. So I can represent each and every bit hexadecimal with the 4-bit binary. A means 1010. B means 10. This is how, if you are declaring any variable in the Verilog, it will store in the memory in the same way. Okay. So there is another last. These are the different ways to define a variables. So if you define, no, it will throw syntax error. If you define 2 tick B and if you are giving 110, and then it will throw error. So it won't discard anything. It will throw some syntax errors. That error might be depends on specific version of the tool, but this is not the correct way to define a variable. Tools will throw error. Few tools will discard, but that depends on the tool versions you are using. Okay, but ideally this is not the correct way to define a two-bit variable. You can extend, you can give 64 also. If you see, let's say if you give A is equal to 64-bit binary or a 64-bit hexadecimal, you can specify, and you can give A, C, D, B, 2, 3, 4, something like that you can give. 64 means divided by 4 means 16, 2, 3, something, some number you can give. So it will allocate 64-bit memory. So 32-bit is default, we can say. Okay, 32-bit is not maximum. 32-bit is default. So if you are not allocating use anything, if you are writing any, let's say A is equal to, if you are using 32, the number, let's say 100. So it will use 32-bit memory by default, not the maximum. Okay. And let's say if you are defining a variable, let's say you are defining A is equal to, without giving any number, if you give H23, you are not defining how many number of bits should be used to store the value of A. So in this case, tool will use the default one, 32-bit. It will use the 32-bit memory, 32-bit location memory. Okay, 32 bits, and then store this hexadecimal value 23 in the 32 bits. If you are not defining anything here, okay, so in that case, it will store in a default one. These we can say integers. You all might aware in the C language, right? Integers. So the same way integers here it is 32 bits default. If you're defining any variable with integer, a equal to some 243, then integer means it is taking 32 bits by default. Okay. So till now we discussed only positive numbers, right? We want to give any negative number to variable a. Let's say this is a variable, and if you want to give, let's say if I'm giving 60.24, so it means it will use 6 bits to represent the value 24 in the memory location, the value a. So if I want to define minus 24, then what is the way? Minus 6-bit D24. Okay, it is not something a is equal to 6-bit D minus 24. So this is the wrong syntax. It will throw error. So you have to give the symbol before 6D itself. Okay, not before 24. And here also, these are all defining a numbers, right? If you want to store a variable with a string, let's say string is always defined with the double quotes, then it will consider like it is similar like C language. Let's say if I say a is equal to hello, so you should give this string in between the double quotes, then only it will consider as a string. Otherwise, it won't allow you. Yeah, that is a possibility. So that allocation will be taken care by the rule, but this is one possible allocation. You're giving 2 tick B and 3 tick B1. So it will something like, if you say 32. So this 3264 is depends on the machine, because if you're using a 32-bit processor or 64-bit processor, there is a definition, right? How many memory locations each address lines and data lines. Based on that, the size of each address location will be depends. So there might be a chance of each memory location having 64 bits capacity. Okay, let's say you have data lines, 64 data lines. So then I can create a memory location with 64 bits. That's my wish. That depends completely on the system. Okay, but as per the Verilog syntax, it will use only 32 bits of 64 by default. Okay, we cannot estimate that okay, this value is stored in this location, this value is stored in this location. There might be both of them stored in the same location, or else they might be both of them stored in different locations. That we cannot guarantee. Okay, so this is a way to store strings. Then next we will discuss some keywords in the Verilog. Okay, so before that we have to discuss data types. Those are 5 consecutive bits. How does tool know which one is? I didn't get that. 5 consecutive bits. No, if you are giving A is equal to 2 tick B 0 1, right? So it means these 2 bits are set. It doesn't mean whether it is storing in 32-bit memory location or 62-bit memory location. It will take these 2 variable and assign it to A, and it will, let's say, it might have considered these 3 bits 0 1 0 for B. So this is the mapping tool is doing. So whenever you are using the variable A, let's say if I perform C is equal to A and B, then it will take the value of 0 1 from here, and it will take the value of 0 1 0 from here, and it will perform. It may or may not be consecutive. That's what I'm trying to tell. It will just assign that variable to that memory location. Okay, here, like unlike in C language, we have many data types in C language: integer, characters, string, something like that, everything, right? But here, what are the options for every variable? Whatever the variable you're defining, there are only 4 combinations, only 4 options. Let's say if I define a variable A, so you can define A with 0, 1, Z, X. These are only 4 possible values you can fill with the all the variables. 0, 1, Z, X. That's it. So whether it is integer, input, output, whatever. So only 4 type of data, 4 combinations. These 4 are available. Okay. Okay, so variables you are defining in a Verilog will be either, let's say if you have a circuit. Here in this circuit, I have AND, OR, and here I have an AND gate. Okay, so these 2 are going here, and these 2 are inputs. These 2 are okay. Let's say I have A, B, C, D, 4 inputs. So this is my circuit which I want to write a code in a Verilog. So let's write in a simple way. Okay, this is Z. This is my output. So before writing any code in a Verilog, first you need to identify inputs and outputs first. Okay, so identify the inputs. What are the inputs of the circuit? A, B, C, D. So in Verilog, each and every circuit we can call it as a module. Okay, so this is the syntax. Module is the main head of the every circuit. So if you want to write anything, first you have to start with module. And module name. Okay. So this is the, so tool will understand this is the start of your logic. And if you give an end module, so tool will consider, okay, the definition of the module is ends at this point. So remaining everything is a body. Okay, module is a keyword and this is the name. So let's say if I want to, this circuit is, let's say circuit one. So module, circuit one. Okay, this name you have to make sure it should not, you should not use any keywords which are already present. Let's say input, output, so, those names you cannot use in the names. This name should be should not be present in the tool internal keywords. It should not match with the keywords, data types, register, one tick digit or something like that. It should be unique English word. Then inside that you have to define all the inputs first. Okay, input A, B, C, D. You can define in this way, or else you can define A, input B, input C, input D. Either way you can define. Okay, so I declare all the inputs in a single shot. Then I'll declare output. Output is Z. See, I'm not giving any length of this each and every variable. It means each bit A, B, C, D is single bit inputs. Okay, if I want to give 32-bit number in A, B, C, D, and if I am expecting 32-bit number in Z, then I have to define in such a way that this is the integer I can say. Integer A, B, C, D. Okay, so then I can give 32-bit number in the ABCD. So now I'm defining as input, right? So all the variables input, output, register, wire. These are most commonly used data types in a Verilog code. Input, output, reg, wire. Okay, so all by default only one bit. So whatever the variable you're defining in this keyword with this keyword input, output, reg, wire. So all are by default one bit. If you want to give multiple bits with the input output notation, not 32 bits, so I can define in where input, let's say 3:0, A comma B comma C comma D. Okay, after input there is a space. Okay, there should be a space. After that, A, B, C, D. So now each and every input, whatever the inputs I am giving, right, all are 3-bit inputs. So what is the expectation then? How you are defining Z? Output 3:0 Z. Got it? So this is the way to define single bit and multi-bit variables. Okay, so input output I defined. Then you see this is AND one. Let's say we can name it AND one, and it is OR one, and it is NAND gates, right? So here from AND gate to NAND gate, you're connecting, right? So this we can call as a wire. See, this the wire is starting from internal and it is ended the internal. But this in why we call as inputs, these are started from the top level. So these are giving from the outside. Okay, and why it is called as output, it is going out from the design. Okay, but these are internal wires. Okay, if you see these output of the, it start from the output and AND gate and it ends at the input of the NAND gate. Here also this wire too, it starts at output of the OR gate and it ends at input of the NAND gate. So those we have to declare as a wires. Wire. If it is a single bit, then let's say W1 and W2. This we can name it as W1. This we can name it as W2. Okay. So now, how to write that code? So here, so first what you are doing, you're ANDing A and B and you are giving that to wire 1. See, wire 1 is taking that output of the AND gate to the input of the NAND gate. So wire 1 is the intermediate one. So first, what you have to do, you have to take the inputs, right? So wire 1 equal to A and B. That's it. Okay. So then wire 2 is output of the OR. So wire 2 is equal to C or D. So now what you're doing this wire 1 and wire 2 and giving this to NAND gate output, which is assigned to Z. So now Z equal to wire 1 and with wire 2, this is not AND operation. It is NAND. So you have to give this one. Semicolon is mandatory after every line. Okay. So that's it. You are assigning a value of Z. Then end module. So after end module, you cannot give anything. Okay. Understood? So these are this is some basic way of writing. So let's say I defined inputs here, outputs here, wire here. After that, if I define input, C again. Already I defined and I try to define again, then it will throw some error. Like variable C already defined. Okay. And this is a simple way to write Verilog code. Okay. So now let's discuss one small topic related to strings. Let's say if you are defining string 1 with hello world, let's say hello. So now the length of the string should be each and every character in the string is 1 byte. This is exactly same as a C language. So 1 byte means 8 bits. 8, 8, 8, 8. Total how many bits you require? 40 bits to store this small string. So you need to declare that str1 as a register. str1. Before that, how many bits you have to give? 39 is to 0. str1. Then you can write that str1 equal to hello. Okay. So this is the way to define that small strings. Usually, mostly we won't use that string notations and string initializations. And we discussed input, output, wire. Okay. So next data type is a register. Okay. Here, if you see, your circuit is entirely combinational one. So you need not to use this keyword register because your circuit need not to hold any value. If you want to use, if you let's say at the output, the same circuit, you are using a flip-flop and clock is coming somewhere. CLK another input. This is D. Let's say this is Q. So now you cannot declare Z as a just output. Okay, you can declare Z as output along with reg also, because whatever the outputs which are coming from the flip-flop, those you need to declare at the registers. Okay, if the flip-flop is present internal, it means after that AND gates, let's say you have the register D, Q, clock, and this output is giving to NAND gate. Other input of the NAND gate might be direct OR operation. Let's say then A, B, C, D, and this is clock. this is flop, and these are the gates. Then you have to declare these Q, means this is, let's say, wire 1, this is clock 2, this is wire 2, this is wire 3 only, but you have to declare this wire 3 as a registers. So reg W3 you have to define. Understood? Z as it is, output Z, but the remaining wires we declare W1 comma W2. So remember, whatever the wires which are originating from the register output, those you need to declare as a register, right? Okay, because the difference is wire cannot hold the same value for longer time, because whenever the input is you disconnected, it will lost its value. But this register variable you declared, right? So then whatever the value of Q, it will take it. So that is the difference, because the Q is always holding its value, previous value, until the clock comes in. So these are the main types of data: input, output, reg, and wire. So like each and every variable you can declare with a size. So if you declare input A, then we can call as scalar. So it means simply get a single bit. So if you define it means it is a vector. It is a multi-bit input. Same thing we can define register also with multi-bit. B. Okay. Same thing wire also you can define 4:0. So if you want to access single bits, so only output of the flip-flop you can use. Flip-flop, and so mostly you cannot directly write the flip-flop. So usually what will happen, to write the flip-flop definition, you have to use the always block, which I will explain later. So in that always block, whatever the value you are using, Q or T, so that you need to declare as a register. So it means we can say in always block, whatever the value you are assigning, and so whatever which variable you are going to assign, right? That variable you have to define as a register, because that D flip-flop definition you cannot directly get from any symbol. You have to write the D flip-flop. While writing the code, you are assigning Q value with something, whether D or one tick B0 or reset or clock, whatever you are going to assign. That Q should be declared as a register. Then only register will be replaced with that always block. Otherwise, latches will be inserted. Okay, that is the difference. So simply we can say wherever the outputs you are using of the register, right? So those you need to declare as a registers. So there is a wire which is created automatically with that register keyword. But if anything, if you use a register, if you use the wire, only wire will be created, but its functionality will be different. Its usage will be different. Okay, but oh, there's some problem with mic. I think it doesn't have any charge or what. Okay, so if you are defining, let's say, multi-bit, right? So this is multi-bit A, but you need not to access A at all the same time. So I can perform operation C of 3, something like this, equal to A of 3 and with B of 1. This also I can say, I can do it. Okay, you can use single bits in the this we can say bus. Okay, if any bit, any variable having multiple bits, then we can say it as a bus. You can access each and every bit separately with the square bracket. This is the syntax for the accessing bus. And not only single bit, you can access the range also. Let's say C, I can write 1:0. So it means C, if you see, we defined as a 4:0, right? So it means C has assigned 5 bits. 4, 3, 2, 1, 0. I can access 1:0. So these two I can access, and I can perform A of 1:0 ANDed with B of 1:0. So now what will happen? So A has some memory. So here let's say 10. This is B, 4 bits, 3 bits and 4 bits, 0, 3, 2, 1, 0. So here I can say 1, 1 I have. So now what will C will do? So it will AND it with 0 and 1. 0 and 1 ANDed with and then answer result will be stored in 0. Then 1 multiply 1 and 1. These both will apply to a AND gate again. Okay, these both will apply another AND gate. These both will apply another AND gate. This will store here and this will store here. 1. Okay, that's why I say bitwise AND, this AND. Is it? Okay, one second. I think looks like there is no charging. I'll just stop sharing. Just give me one moment. I'll connect with my headphones. So now it is clear, right? My voice. Okay. Okay. So we can declare arrays as well in a very long, like in C language. So currently, if you define, let's say, a while with single bit, just wire double while. So it means memory Y is allocated. Okay, so 1 bit is allocated to the Y. So if I define 3:0, of y, if I can say. So y is a single variable. So it means single. Okay. All the 4 bits are assigned. See, this is y. So these 4 bits, 3, 2, 1, 0, is assigned a memory and you can access y. Okay. If you access y of let's say 1:0. So that means 0 and 1 of the y will be accessed. Okay. So this is the one way of defining. Let's say how can I define array? So I can say y of let's say I am giving 3:0. Okay. So now observe the difference between these two. Earlier, all the 4 bits are assigned in a scalar like a vector quantity. See, so 4 bits are assigned, and if you access y, all the 4 bits will be accessed. Now, let's see, I'm giving 3:0 outside. So now what will happen? Let's say this is my memory. Okay, but here this can assign to y3, this can assign to y2, this can assign to y1, this can be assigned to y0. But if I given this one, right? So here y of 3, y of 2, y of 1, y of 0. In this way it will allocate. So it means single variable assigned in a sequence way. But here if you see y of 3, so it means the array kind of thing. So it will store in a different location. And you will understand with this example, y of 3:0 and y of 1:0. So now what will happen? You see, so now if I say this is my memory, okay. See, y of 3:0 means two locations will be created, but 1:0 means two locations will be created for the y. So it means this is y of 1 line and this is y of 0 line. Each and everything has a 3 bits again. 3, 2, 4 bits again. 1, 0. 3, 2, 1, 0. Understood? Now I created an array with a multi-bit locations. See, if I'm giving whatever the value I'm giving after the y, it means two different locations it will create. So whatever the number I am giving before y, so it will be the length of each location. Understood? This way we can create arrays. And you can use y of 0, 1, 1, 0, something like that. And there are another ways to define these variables. Let's say we have a module. Okay, earlier, like say we can say it as a design one. Okay. Here what you can do, you can terminate it and you can give the inputs, outputs, wires, registers here and assign some variables, A, B, C, D, something like that. Okay. But there is another way we can define simply after the design. After the design, you can open from bracket and you can give A, B, C, D. And then you can declare those ABCDs, input A, input B, Y, something like that. So here from the top itself, you will understand how many number of inputs and how many number of outputs and how many number of variables at least present in the module. So the significance of this having the variables at the top, you will understand when we go into module instantiations. Okay. So as of now, this is another way of defining a module. And instead of here, you can directly declare here itself. Input A comma input A comma B, input B comma input clock comma output Z. Remember, while declaring here itself with along with the module, you cannot declare multiple variables at the same time. You go inside, then you can define input A comma B comma C comma D, something like that. Okay, so these are all three different types of defining a module. The significance of each and every one you will understand later. Okay, we'll write a small code for we have a register, we have 4 registers. Each register has 16-bit wide. The length of each register is 16-bit and you have 4 registers. You have to write a code and you have to assign some values of the each and every register. Okay, that is the task. So now just write a module. And let's say range 1 I can give. I can define clock. I can define reset. I can give some data which I am going to send every register. Okay, as of now, these are let's say, and some m underscore range. This is my register. Okay. Now declare all of them. What are the inputs? You can declare inputs. Class is input. Reset n is input. Data is input. But the temperature is register. But how I am defining? So what I am asking, 4 registers each are 16-bit wide. 16-bit wide means 10:0. 4 registers means temp underscore range 3:0. See, total number of registers 4. Each has 16-bit wide. That's it. Okay. So now send the value to each and every register by using first you need to write a code for flip-flop. Okay. So remember one thing, to write a flip-flop, what is the condition? Whenever the clock pause edge is detected, pause edge or negative. Okay. So then only value of input is going to the output. D is going to Q. Otherwise, it will not go to Q. Okay. So here temp underscore range is your Q of the flip-flop. So now you have 16 registers. Sorry, you have 4 registers, each are 16-bit wide. So it means while initializing any register, how many bits you require? Data, input data is 16. So now I can decide. So I can replace this data like input. I can say input. How much is the length? 15:0 data. Okay. So now just observe the code for the flip-flop. So this is always block at the rate, you can say to give positive edge. See, positive clock means whenever this always block will start executing the line before it. See, after that you have to give begin and end. Okay. So now what is always block? This always block will execute only if the value, only if the condition detects in the circuit, only if the positive edge is detected in the clock. Okay, this always block will trigger only whatever the condition you written in the brackets. So positive edge of the clock you return. So it means the positive edge of the clock returns, what you have to do, let's say you are designing a synchronous flip-flop. So it has a clock, it has a reset. Okay. So it means synchronous clock means even the reset also should go along with the clock. So first you have to write if reset, if you are giving reset 10. Okay. And you have to write along with begin and end. So what you have to do, you have to initialize all the registers with a 0. Okay, not only single registers, all the 4 registers you have to initialize with a 0. So now you have to write, you can write for loop. This for loop syntax is similar to the C language. You need not to learn anything. I is equal to 0, I less than, see the length is total number of register 4. Excuse me. I less than 4 and I equal to I plus 1. Okay. Remember, for each and every loop, you have to give in a begin and end. Begin. So now what you have to do? Temp, that is your register, right? Temp underscore range of I is assigned to 0. Okay, then end. So this is a logic for reset is done. Okay, end. So if reset is not detected, then write else block. Else block it is same. Same again, use a for loop. Same for loop you can use and begin and end. Now temp underscore range equal to data. Here both of them, sorry, range of I is data. So data is a 16-bit wide, and each you are giving 4 registers. For I is equal to 0, I less than 4, I is equal to I plus 1, and begin. So temp 0, the register temp underscore reg of 0 is assigned with data, 16-bit data, and then after some time, again this loop will turn back and it will again assign the same value. So this is the way to write a code for a flip flop. Just I'm telling the example of the flip flop. So I think after that we have to data types. Okay. So in Verilog, we have some keywords. Few of them we already explained, like input, output, reg, wire. Okay. Along with that, we have another keywords like always, case, begin. So I'll explain one by one. So first, go with begin and end. So begin along with it. So this is the most important keyword which you these are required if you're writing any loops. This will be used inside the loops like while loop, for loop, if conditions, everywhere with any condition statement having at least single line, we have to use this begin and end. Even the always block also you have to use the begin and end. Okay, so begin and end means if you are writing any small code which should execute with certain conditions. Okay, whether it may be if loop, for loop, while loop, always, whatever. So the begin and end you should use if you're writing any conditional statements. Then if else you already aware, right? If the condition and begin and end you have to give and then you can write else, and you can give begin and end. In between, you have to write body. Okay, this if syntax is exactly same with the C language syntax. If loop, for loop, while loop, everything is matching with the C language. No need to learn anything new. Okay, and another important keywords are edge. See here in if loop, you can consider, let's say if I am having a variable a. Okay, this I am sending from the outside, not from the inside the circuit. This is the input. Okay, if a is equal to, I can compare 1, or I can compare if a is equal to 0. Only these two comparisons I can do with the if loop. Okay, so but now in digital electronics, what is my requirement? If you see, if I write a flip flop, or else if I write any case, so sometimes there is a requirement of you have to detect the edges also. See, this is 1 and this is 0 and this is edge. So I don't want to do any operations on this 0. I don't want to do any operation on this 1. I just want to do some operations on this edge. So it means whenever a is changing from 0 to 1, I need to perform some operations. That is my my requirement. So if that requirements we cannot meet with the if, else, while, whatever. So these kind of requirements will be met by with the edge. So I want to do some operations on both the edges. Let's say positive, negative, doesn't matter. So whenever the change is happening in the input, let's say whenever a is changing, I need to perform some operation. So what I can say, always I can write, always at the rate, I can say edge a. So it means whenever positive edge or negative edge, whatever detects this edge a is going to be 1. Like same way in if loop. Let's say a is equal to 1, right? If see, you can consider 0 equal to 1. Same I can replace if edge a. So then what will happen? Whenever the edge means 0 to 1 or 1 to 0 is happening in the a, then this if loop becomes 1. It will execute the code inside the if loop. So this is the importance of this edge keyword. So that edge we can decide, we can divide into two categories: pause edge, neg edge. Okay, same if you write if pause edge a, you can write. Okay, then positive edge of the a is detected. Whenever the positive edge of a is detected, then whatever the code you are writing below this, if this will be executed. Okay, and the next thing is always block. This is a very important one for writing the flip flops, which we are using to write the code for flip flop. Because this always block significance is edge pause edge, let's say at the rate pause edge of CLK. So how this always block is differing from if? Let's say if I write if edge, let's say pause edge. Yeah. So while executing the code one by one, if the positive edge is detected, let's say this is my clock, the positive edge is detected, the code which is present below this if will execute it. After that, it will go and it will continue. If the next edge detected, then this will not execute because this way already executed only one time. But in conventional flip flop, you have to repeat this one until and unless you receive the call. You understood? So if loop will do the same thing, but only for the first stage. So let's say if you have the clock, okay, and if you're writing with if pause edge CLK, then on the first positive edge, this if loop will execute begin end. You write some code for the flip flop and it will execute. What happened will when it will second, third, fourth, fifth edge is receiving. So this if block will not be executed. So this always means even though you write in the start or middle or end, wherever you write, okay, So whenever the pause edge of the clock is detected, this always block suddenly comes into the picture and it will execute the code, whatever you written. Begin inside the beginner date. It will execute whatever the code which you written in the always block. Okay, after that, if you write some another if block, which is completely different, a is equal to 1, some code you are writing. In between, while executing any code, while doing any operation, suddenly if you detect a clock, right? So then the tool is coming into this always block and execute this code and it will continue its operation. Understood how the always block is deciding the factors. See, that is exactly suited with our flip-flop definition. See, whenever the clock receives, it doesn't care about the other combinational outputs. It is just sending the value of D to Q. So which is matching with our flip-flop definition. That's why we are using this always block while writing the definitions of the flip-flops. Then that is important. And the next thing is case statement. Okay, let's say this is my input. Until and unless you stop the run at the end of your execution. No need to define anything definition, right? So until and unless end of your run, as soon as you are giving the positive edge of the clock, it will execute. So if you want to stop that always block, you have to cut that positive edges of the clock. If you stop the clock, then this always block will be terminated. That's it. Okay. To stop that always block, you have to stop the clock. Whatever, I mean, not the clock, whatever the variable you are giving at the pause edge or negate, right? If you stop that edges, then it will not execute. In this case, only way to get out is the clock. Okay, in the specific case, we're giving some variable, so you need to control that variable from the outside. And the next thing is case statement. Let's say you have input A. Okay, let's say you have single bit inputs A, B, C. You have output Z. Okay, so now I'm writing code Z equal to A question mark B colon C. It means whenever A is equal to 0, B will go to Z. Whenever A is equal to sorry 1, B equal to going to Z. If A is equal to 0, C will go to Z. So what is the operation here? Mux will be created. If you write a code, this will be selection 0 and 1. If it is 1, then B is going. If it is 0, then C is going. Output is going to Z. So this is a replication. If you have a single bits, you can write in this way. Let's say if you have this input of 3-bit image. So A is 3-bit, B is 3-bit, and C is also 3-bit. Z is also 3-bit. Then you have to write the same code for 3 times. Z of 3 equal to A of 3 question mark B of 3 C of 3 Z of 2. Or else you can put a for loop for I is equal to 0, I less than 4, I equal to I plus 1. Begin Z of I is equal to A of I question mark is B of I colon C of I. End. Okay, this for loop will reduce the user effort to write the code. But if you execute this one, right, tool internally will convert this for loop into 4 times. See, that is a real case, right? Tool cannot directly understand the for loop and execute. It will elaborate these for loops. These for loop, while loops, do while loops are introduced for user convenience. Because you cannot write multiple times with your hand. You can write only one time, then tool will convert this for loop into 4 times. So it will elaborate in the 4 times. Z of 3, Z of 2, Z of 1. So 4 commands. So if you have multi-bit inputs, instead of going with this question mark operator, you can go with the case statement will be used in a certain case. Let's say you have some selection A of select, let's say is to 0. This is selection, and based on the value of A, digital value of the A, the question which is asked here, right? So you see here, let's say consider this case only. If we have the case where if B is equal to 8, then we want A is equal to C, and then else we want to use A equal to C. So if the specific cases we have, right, so then case statement will be best solution. Let's say you declare this variable B, okay, it is 8-bit, which is a selection, and again input A, sorry, A is output, right? Here is any value. Then C comma D are the other single bit input. Then output is A. Okay, this is my question. This is the question, which is this is my requirement. Okay, and this is the variables which I declare. Now, if you write with a question mark, then you cannot write, because what how you have to write 8 means binary 100. Okay. Now you have to consider all the 4 bits, and you have to write 4 times 4 different combinations as well. Okay. So now, so with this case statement, how we can write? You see, if I write case, okay, I can give this B in the case, and then I can write all the combinations. So B1, 8 means what? So 100 binary. So if I receive 100, then I can write whatever operation I want. A is equal to what is the requirement, or C, right? A equal to C you want. C. Then after that you can exit, and you can write a default case at the end. Let me check the syntax. 1 second. And then you have to write a default. Default what you are expecting, A is equal to B. That's it. In simple way, we can write with the case statements. So what is the significance of this case? So here, if you consider case of some variable, so now the tool will consider all the combinations of the variable. So let's say B is a 4-bit variable, right? So then 000, 0001 until 1111. So total 16 combinations it will consider. And you can write whatever the combinations you want to perform. Let's say in 16 out of 16, only for 8 combinations or else only 2 combinations I want to perform some operation, specific operation. For the remaining all the combinations, I want to perform another operation. So then this case along with this default will be used. And remember one thing, whenever you use the keyword case, okay, you have to use this default, otherwise you'll get a syntax error. Something case statement without a default case. So each and every case statement should have default case. That is a mandatory. Okay. So inside first you have to write specific operations for specific combinations. And at the end, so default case is for all the remaining combinations. Okay. And for this case statement, you need not to give begin and end. See, case of B you are giving. And then, so whatever 1000 you are giving, directly you can write. And if you have for this 1000 case, you have multiple lines, then you have to give in begin and end. Begin end. So this begin and end will be used for different cases, not with the total case. Okay. Default case also same. Let's say if I have this variable B, and sometimes here only I have only one specific combination to do some operation. For all the remaining combinations, I do some other operation. Let's say for all the 16 combinations, I have some operations to perform. So then I have to write everything 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, something. All the combinations, if I write something, then you will get a doubt like what we have to write for a default case. In this case, if you have all the combinations, default case is a dummy case. It is just only we are writing for a to avoid the syntax error. Anyhow, if you write all the combinations, then tool will not enter into the default case. If you skip any combination of the case variable which is present in the case statement, then only it will enter into the default case. Understood? If you write all the 16 combinations here with 1, 0, 0, 0, 0, 1, something like that, then it will never enter into the default. So in this case, you can write some a equal to 0, 0, 0, 0. Simple. Or else a is equal to 0. If it is single bit, a is equal to 0. So it is just to avoid the syntax errors. If you have all the combinations. If you have only few combinations you left with the default one, then this default statement will execute. If you give that input combination. Okay. These are some important syntaxes and everything. Take 15 minutes break. After that, we will I will explain different type of modeling coding styles. So we can say structural, behavioral, and gate level. We have total 3 type of default case statement of input or while. We define them and not enumerate them. So default, these ZX will fall into the default case category. If you consider all the combinations and from the outside, if you are giving the stable values, then the tool will not enter into that default state. Okay. In the from the output point of view, and whatever the combinations I explained is zeros and ones. Okay. If you consider Z and X also, so because most of the times you need not to write expressions for Z and X. Okay. In that case, it will consider Z and X also as a default thing. If you give Z, right, 2-bit Z, something like that, then it will enter into the default case. Okay. Default cases will depends on whatever the values you written in the normal case statement. Let's say if I, and don't forget, you have to give some 4-tick B0. If you're writing in binary, right, in the case, you have to give 4-tick B0 always. And let's take this question. So let's say if I define while of W1, it means it is a single bit. And if I write a case of W1, it means it will consider all combinations of W1, 0, 1, Z, X. And let's say if I write only 1-tick B0, then I write some operations. If it is 1-tick B1, I write some operations. If I given, I can give 1-tick BX also. I can write some operations. I can give 1-tick BZ also. I can write some operations. Okay. If I give default, then it will be useless. If I skip these two, the Z and X will fall into this default category. Usually, you cannot send these X's and Z's from the outside, these wires or inputs. Usually, you won't send from the output. So that's why I explained only with the zeros and one combinations. If you intentionally send zeros and Z and X, those will fall into the default category. Okay, in general, we won't send that X and Z from the outside. Usually, we'll send zeros and ones. So if you intentionally send X or Z from the outside, then it will consider as it will go into default category. Understood? Is it clear, right? Here you have to understood the real scenario and the theoretical analysis. Okay, so let me explain that real scenario. 0, 1, Z, X. So in the silicon, you have only two options, 0 and 1. These Z and X we derive. Okay, X means if you are not sure about whether it is 0 or 1, because in silicon 0, 1. Okay, 0 means 0 volts, 5 means 5 volts. And let's say you are defining a threshold levels of, let's say 0 to 2 volts is the input voltage, then you are treating as the 0. If the output voltage, if the input voltage is 3 to 5 volts, you're treating it as a 1. Or else we can say 0 to 2.5, it is 0. It is 2.5 to 5, it is 1. So it depends on your interest. Okay, but if the input is not stable and it is jumping from 2.4 volts to 2.6 volts, so like say we are drawing a waveforms like something like this straight lines, right? But in real scenario, if you are getting something like this, here because of the threshold voltage, still it will detect as a 0. Here because of the threshold voltage, still it will detect as a 1. But what happened if these spikes are larger at some times, smaller at some times? Then here is from here, this point to this point, you can say. See, here this is my threshold. So here in this case, I cannot guarantee whether it is 0 or 1 because it is jumping from 0 to 1 within a given time. Because see, if I'm able to detect whether 0 or 1, it should hold its value for at least some particular time. Let's say it might be 1 microsecond, it might be 1 picosecond or 1 nanosecond, whatever. But for at least some given time, it should hold the same value without jumping any values. See, if I detect the timestamp is, let's say, my 1 nanosecond. But in between the 1 nanosecond, if its value is changing from 0 to 1, 1 to 0, then which value I can decide whether it is 0 or at 1. Then in these cases, in system, not in the silicon, we can mark them as a X. If you are unable to decide whether it is 0 or 1, that is X. Z means if you are not connecting any input to the any gate, so that we can call it as a Z. And if it is not connected to anything, let's say if there is an AND gate, okay, so this is a circuit, you are giving inputs A, B, Z. Let's say this is detected, this connection is deleted from this gate. So now what is the value of Z you are getting? You will get 0 only, right? So it is not connected to anything. So it means, but this case, this 0 is not equal to, if you're applying 0, 1, then only you will get 0 also, right? If it is connected, still you will get 0. But there is a difference between the 0 which is coming from the inputs, the 0 which is not connected anything. So to distinguish that 0, we are defining this high impedance state. So this 0, Z and X, you can get only in the system. while generating patterns or while simulating patterns, whatever. The Z and X will not come into the picture when you go into the silicon. Okay. So I hope this will clear the doubt, whatever you asked Z and X. So it means if you are declaring a variable W1 and if you are not defining, initializing with any value until 1 microsecond, it means what is the value? It may be 0 or it may be 1 based on the glitch. So we can treat it as a X. Okay. So next we will discuss some coding styles. After the break, we'll discuss some coding styles in a very long. So we have 3 type of coding styles: behavioral, gate level, and 1 second. Behavioral modeling, gate level modeling, and structural modeling. So those 3 type of coding styles I'll explain. So with that, I think we can close this very last session, because if you've gone through this, if you understand these keywords and the coding style, then you can mostly will understand whatever the code written by the designer. So up to that, it is fine as a DFT engineer. Yes, W1 will be X up to 4 nanoseconds. X in the sense, it is in the silicon, it is not throwing X. It might throw 0 or it might throw 1. That we cannot guarantee and we need not to consider. Yes. It may be 0 or it may be 1. You cannot estimate, that we can say. You cannot predict that value, whether it is 0 or 1, because you are not applying any valid input. So whatever the value which is on W1 is unpredictable. Okay. So I'll be back in 15 minutes. We will start 3 type of coding levels: structural, behavioral, and gate level. Okay. Welcome back. So before going, so generally we have 3 type of modeling. So modeling means the way of writing the code. Okay. Structural, data flow, behavior. Structural or gate level. Okay. So before explaining these 3 type of data types, data flows. So first you have to understand module definition and module instantiation. Okay. So module definition means you have to start with the keyword module and name of the module, and then optionally you can use this brackets. Okay, if you want to declare variables here itself, you can use it. Otherwise, you can directly declare here and end module. Okay, let's say I written a code for a half adder. Let's say I am designing a 4-bit parallel adder. So it means how I write the code: module adder underscore 4-bit, the name. And the inputs are A comma, B comma, AB are the inputs and C is the output. Okay, here you need not to declare all the bytes in the module definition column. Only you need to declare inputs and outputs. If any bytes you can directly declare in the runtime. But what are the input? Input of 3:0 of A comma B. These two are inputs. Output 3:0 of C. Okay, so in order to design a 4-bit parallel ladder, first you have to design a full ladder, right? Because you are using 4 full ladders connected in such a way that you can get 4-bit parallel ladder. So do I need to write a code for all the full ladders and connect them together, or else I have another shortcut? I can write only code for one full ladder, because if you observe all the full ladders, only inputs are different. Remaining logic for the full ladder is same, right? Okay, so now what I will do, I can write a code for a full ladder. Here you see. Okay, so let's do in this way in module. Here I'll open another module. This name full adder. Okay, here also A, B, C. Full adder means how many inputs? 3 inputs and 1 output. Z. So remember, this is full adder. So it means it will require 3 inputs and it will give only 1 bit output. Here you can declare in the same way. Input A, B, C, output Z. So for full adder, you know the equations, right? For sum, the equation is A XOR B XOR C. For carry, AB plus BC plus AC. Correct. So now you see here output is, let's say, sum carry. Two outputs we have. Okay, sum carry. So now equation for sum is, and we can directly assign A XOR B XOR C. For carry, what you can do, you can directly write A and B bracket or B and C bracket or A and C. That's it. End module. Okay, I have the full ladder definition now. Okay, so now I have to define a parallel ladder by using the full ladder definition. See, if I directly define parallel ladder, I need to write the same code for 4 times in the main module. But instead of that, I write the definition only 1 time and I use this module in the main module. So let's say this is this full ladder. So this we can call definition. Okay, this is definition of the module. Now, if we want to use this module in the another module, then we can say it as an instantiation. Okay, so that the syntax for the instantiation is, first you have to write a module name. Which module you want to instantiate, and then space instance name. Because full adder I have only one name, but if I use full adder for 4 times, then I need 4 different names for the 4 full adders. See, that's why module name is 1 and the instance names will vary from each and every time. And then you have to map each and every inputs and outputs of the lower level module in the higher level module. Understood? Because if you see, you have 1, 2, 3, 4, 3 inputs and 2 outputs. So from the, if you instantiate this module in the main module, you have to give 3 inputs to this module and you will get 2 outputs. This mapping you have to do properly. How that mapping will happen? To see here, A dot A of A is to 0. A of 0, comma, dot B, sorry, dot B of B square bracket 0, comma, dot C. For the first full adder, what is the third input? 1 tick B 0. Understood? So let's write it in a way. So the module name is full adder. Instance name is I can give F1 or else F0. Okay, I'll open the bracket dot A of 0, comma, dot B of B of 0. So imagine the full adder circuit what we drawn earlier. See, 4 full adders are there. A0, B0 is going. C0 is always 1 tick B0. Here A1, B1. And the third input is carry of the previous one. Okay, and for the first full adder, C is 1 tick B0. You understood, right? 1 tick means I can only assign 1 bit. So 1 bit, that is binary 0. Binary 0 is going to C. This is the first full adder instantiation. Then sum. What I have to do with the sum? Sum I can directly send it to C of 0, right? Understood? Because here the sum is directly going. For all the cases, sum is directly going to C. C of 3, C of 2, C of 1, C of 0. The sum is always directly going to the output. Here C is output, not carry. And let's see what is carry is doing. This carry, you have to send it to the C input of the next one. So you have to declare a wire of this 1, 2, 3 wires are fine. Wire 2 is to 0, which is for carry. Okay, and remember one thing, you can use the same names in the both the modules. So there is no overlapping of error kind of thing. So you can use the same name in the main module and then the sub module. Okay, same carry name I can use. I can assign same name. I can use the same ABC and everything. Here the carry is assigned to carry of 0. And after this, another one, and proceed with the parenthesis. Then this is my full adder. Next, write another full adder. This I can say F1 because I'm using the same full adder, but the operation is different now because I'm changing the inputs. See, if you see A, now A is assigned to A1 of the top module. B, same B of 1. C. Now what is the third input? Third input of the full adder. Carry of the previous adder. See, C is carry of 0. All inputs are done. Then, sorry, this syntax. First comma and then dot. Dot. Then sum. This sum what I have to do? Uh, Sorry guys, there is some network issue. I think that's why. Up to which point you guys listen till what point you listen and previous one? Just let me know. Up to full address F0 is clear, right? Sorry. Okay. Your speaker is, I think I can hear from other. Okay. Can anyone just speak? I'll just confirm whether I can hear from here or other one. Hello?
Hello, sir.
Yes.
Can you please explain this topic for the power concerning?
Yeah, sure, sure. Yeah, sure.
Sir,
I'll,
please explain slowly, sir. We can't understand properly.
okay, okay. I'll start from scratch again. Okay. No worries.
Okay, sir.
Because I think other class they started. That's why it got disconnected. Something. Okay. So I hope you guys understood up to the definition of the full adder, right? Because I won't write it again. So I'll write the 4-bit parallel adder. And here my module name is adder underscore 4-bit. A, B are the input, C is output. That's it. Here input of 3:0, A comma B. Output of 3:0, C. Okay. So I need not to write the full adder for 4 times because I know the circuit. Okay. So write the code for I already assume I already have the code for full adder. So the carry is going into next stage. This is C, let's say this is C of, but if I am using a full adder, the C length should be more than 1 compared to A and B. Okay, because you will get extra carry. Okay, but here is C4, here is C3, C2, C1, C0. A0, B0, A3, B3. Okay, so now first I want to instantiate one full adder. So I can give name, the name is full adder. This we can say module name, and the instance name I given F0 of. So full adder has 3 inputs, sum and carry, 2 out. So dot A. A of A0, comma B of B0. Then the first adder means one tick, B0 I can directly connect. And then sum. Here I can declare while I can say 2:0 carry. Okay. Sum I have to I can directly give that sum to C of 0. That is output. And what I have to do with the carry from the full adder? I can directly connect it to carry of 0. But this is this we can say instantiation. Okay, the definition what we are writing already, that is module definition. This is instantiation. It means in C we can say calling. Okay, then again the second full adder, I have to use the same full adder definition, and the name will be different. The instance name will be different. But here a same, the inputs of the full adder will not change. See, dot a means after the dot you have to write the name of the variable which is inside the module. Okay, inside the internal module. But out inside the bracket, whatever the variables you are writing, those will be available at the top level. So for a simple understanding, this we can say top module. The module full adder is submodule. Okay, so the variables inside the submodule is this, the variable, and the variable inside the bracket is the variable of in top module. Okay, don't confuse in between these two. A of, then now a of 1 comma dot b of then C of what is the third input of the second full adder? Carry of the, that is carry of 0. Then you will get two outputs. Some you can directly send it to C of 1. Carry. You can carry 2 of carry of 1 this time. Understood? In same way you can write F2 and F3 as well. See F3. Let's say dot A of 3 comma B. C. What is the C? Carry of 2 this time. Some is going to C of 3, and then carry going into the last carry should go to C of 4, and then end module. So now you understand the difference between module definition and module instantiation, right? In Verilog we can say instantiation, that at 0. Okay. So this is how you have to use the same one. This full adder 4 times you can do it with a for loop also. That is as your wish. But here if you see, these are not unique. All the instantiation and definitions you see, the first time you are sending C to 1 tick B0. But from second time onwards, you are sending it to carry 0. You go to carry, the carry is going to carry 0, and then the last time it is going to C4. So even if you use a for loop, you have to use if and else loops inside that. So better if if it is multiple lines, 10, 15 lines, then we can go with the for loop. If it is a 4-bit, then directly you can write. If let's say I have 10-bit adder, then I can use a for loop. Inside for loop, if it is I is equal to 0, let's say, then carry equal to, I write another line. If it is the last one, it means I is equal to 9, I can use a different code. For all the remaining, I can use the same code. Understood? And coming to that modeling, let's say if you are writing a code in this way, A is equal to B and C and D is equal to E or F. It means you are using some symbols to represent and or I mean to represent basic gates. If you are using symbols, then we can call it as data flow. Data flow modeling. So it means currently till now we are used only data flow modeling. Okay, but the only difference between these three only while representing basic gates. Remaining code like declaring inputs, declaring output, module definition, module instantiation, all those syntax will be same. Okay, we are using this and or question mark symbol, then we can call it as a data flow modeling. Okay, only while defining basic gates. Okay, then structural means, so what happened, so inside if you are downloading Verilog code, right? So if you see any Verilog code, there is some specific keywords and or not, XOR, XNOR, something like that. So let's say and means you have to send the inputs to the AND gate. It means first bit what you are giving, first variable is the output. This is the default, comma A, comma B. So all the remaining are inputs. Okay, so but not you have only one input and one output. So you can see C, comma A. So it means A is the input of the NOT gate and C is the output of the NOT. So this is the way of representing these basic gates only. Here if you see, this is looking like an instantiation. See, in the internal of the Verilog libraries, they written the code for this AND, what they have to perform. You are just using the definition. But if you are using the definition of internally defined modules in the we can say default modules, you need not to use that notation dot C of C, comma dot A of A, something like that. So this instantiation procedure is followed only for user defined modules. If that depends, if we are using the user defined module as instantiation and you are instantiating tool, I mean internal modules. So that is the way it the both will get different. See, and or not were already in the library. So you need not to use that dot notation. You can directly set output, input, input. Then it will, after this command, so C will be A and with B. That's it. Okay. This is structural. Apart from this basic gates, remaining everything will be same for the structure and data flow. Okay. You won't find much difference. So what you have to understand from this point, so this and C A comma B is equivalent to C is equal to A and B. That is the only thing you need to understand between structure and data flow. Here the R is defined, C is equal to A or B. That is the only thing. Cannot means it is equivalent to C equal to not of A. That's it. Okay. So that doesn't mean if you start a code, you have to write only in one modeling. You can use all three modeling in your single file. Okay, tool doesn't give any warnings or any errors. These are just to understand the different type of flows. That's it. Modelings, we can say. In the single file, you can use structural modeling for one line, and you can data flow for one line, and you can behavioral for another line. You can use the mixed modelings also. Tool will not complain anything. Tool will understand all three modelings. But you need to follow specific syntax while using specific modeling. Okay, you cannot match the syntaxes. Okay, and behavior model in the sense you have to write some truth table. Let's say you have circuit. Okay, and it has 4 input A, B, C, D, and you design one output. Okay, so this is your circuit. So for all the input combination, let's say your output is you have a truth table 0 0 0 0 0 0 0 1 0 0 1 0 and then up to 1 1 1 1. So in K-maps, what we are doing, we are writing combination 0, 1, 0, 1, something like that. Using K-maps, we realize these expressions. So let me explain in a different way. Let's say I have 3 inputs. A, B, C, output is Z. 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. My requirement is 1 here, 0 here, 0 here, 0 here, 1, 1, 0, 1. So if I given this truth table and ask you to write a Verilog code, you have 3 options, right? So first you have to realize this Z equation, okay? Like some A and some A B bar plus B bar C, something like that. You derive one expression based on the truth table, you know, the K maps, right? So you derive the expression for Z. Let's say Z is equal to AB plus A bar C plus AC. Just I write it at a random, okay? AB bar, okay, fine. So how you are defining? You can use how you write the code for this. You can write structural, gate level, and data flow, behavioral. Anything you can write, right? But in behavioral, if you decided to write this code in a behavioral, you need not to write the equation and replicate. You can directly give the truth table, this table. See how we can write. So you can use case statement. See case of A, B, C. So it means 3 tick B 0, 0, 0, then Z is equal to 0, 1 tick B 0, you can say. So instead of deriving into gates and write the Verilog code in terms of gates, you can directly write a truth table. By either you can use by case statements, or else you can use always statements as well. Okay, you can use in different ways. Always at the rate A comma B comma C. Okay, so it means always at the rate, if you write A comma B comma C, whenever there is any change in A, B or C, any of the variable, if you change anything, then this always block will exist. If A equal to 0, comma and B equal to 0, and C equal to 0, then Z is equal to 0. In this way you can write. So this is what we call behavioral model. So instead of expressions, you can directly write a truth tables in the form of case statement or always blocks. So these are the 3 types of models. You need to you need not to tell like this structural, data flow, behavioral. Anyone can use mixed way of all. But the ultimate goal is, even if the designer writes in any format, structural, data flow, behavioral, you need to understand. Okay. But the main difference what you can observe, if you want to write in behavioral way, right, you need not to understand the gates and their behavior. You can design a hardware, any circuit, without knowing any of the components inside the design. See, if I use the behavioral model, right, do I need to know any of the components which needs to be present in that circuit? No, I can directly write a truth table, and tool will take care of what gates needs to be placed in the form of the truth table. So instead of doing the truth table to gate level mapping, you can directly give the truth table and it will map. The tool will map. So what tool will do? Tool will do the K map and it relays the expression and it will map it into the logic. Okay. So the behavioral model is the simplest way of writing code without using that. Let's say if that same truth table we want to design, if that, let's say it is a bigger truth table and it is a complex one. So what you have to do? You have to do K maps. You have to derive the expression, and that expression you have to write the code. It will take some manual effort. But if you use the behavioral, you can directly map the truth table in the case statement form or in the always block form. Okay, so each and every modeling has its own advantages and disadvantages. You designer can select the best way of writing a code among those three. So let's say if you want to write a code for a flip-flop, okay, so he will use behavioral model because that is a more convenient and more understandable and more easier to write the code for flip-flop. If you want to write for some combinations and or gate, then it is data flow will be easiest because using and or not instead you can use a symbol. Okay, and the next topic is blocking or non-blocking statements. Okay, I'll cover it up. But before that, you need to understand one important keyword assign. Okay, that example I'll cover. I'll take one truth table and I write the expression. I try to define with structural, behavioral, and data flow all the ways. So first you need to understand assign statement. So first you need to understand the need of it. So let's say if I write A is equal to B and C, there is some significance for this command because if you see E is equal to, okay, so in Verilog, what is happening? So whenever there is a change in the values B or C, anything, okay, whenever the B is or C is changed, then only this command is executed and this value is assigned to A. Okay, so in the entire code, let's say this is a module and in test bench, you are sending some values to B and C. Okay, so that B and C values are changing something like this. Based on these values, A is going, so and means, so it is 0. Here it is going to 1, and it is going to 0, and here also it is here, then after here it will go to 1. So this is the value of A. So how it is happening? So this AND operation is executed only if there is a change. Okay, only if there is a change in B or C, then only this AND is executing. Otherwise, it will not execute. It will just give the value. Okay, but why this assign statement comes into picture? So if that is input, if that is output or a register, then it is fine. It will hold its value, previous value. If you declare that variable A as a register, okay, then it holds its previous value. Even though it is not a register, if you declare it as a register, then it will hold the previous value. It means one AND gate is placed, and after that there is a latch will be placed. P and Q something, it will instantiate something like that. It will hold the previous value until and unless the next value of B and C comes in. But for that, you can, if you use a wire A, and you are using A equal to B and C, the wire A cannot hold the same value of B and C until and unless you are applying the B and C. Okay, so if it is not executing, the values of B and C, updated values, will not go into the A. For these kind of wires, you need to assign statement. Assignment, it means continuous assignment of A and B to the C. So let's say C equal to assign A assign A equal to B and C. So now the difference is this is one statement, and if I write A is equal to B and C, okay, I declare both the cases, I declare as a wire. Okay, here what will happen? The equal to symbol, what it will do, it will execute the values, it will take the values of B and C whenever they got changed. Okay, and the updated value will assign to A. The same case, let's say this is B and this is C. It got changed. Okay, then in this case, what will happen? Both are zeros, output is 0. Okay, fine. Okay, up to here it is okay, right? From this point, you see input is changed to 0 to 1. So from here, let's say the A is starting from here 0. Both of the inputs are becoming 1. It will become 1. But here if you see at this point, both are maintaining same value. Then this command will not execute again. But as you declare as a wire, it will not retain its previous value for a long time. After that, it is going to unknown state. And then here it is changed, right? This point of time, again the input is changed. Then again 0 is coming. But immediately after some time, it cannot hold the same value for longer time. So after 0, it will throw you excess. As soon as you are maintaining the same value, this command will not execute. So whenever there is a change, see, then it will hold the 0 for some time, and then it will become X. Here again it is changed. Again you can hold same value, and after that again it will throw X. Again here it is changed. Again it will gives 1 for some time, and then it is throwing X. Okay, this is what will happen if you declare as a wire and assign this statement. If you declare as a register, then there is no difference between using assign statement and A equal to B. Okay, understood the difference? If you declare as a register, then both the commands will work as the same. But if you declare as a wire, then this is the difference. So if you use A equal to B, this will happen. But in the same case, if you use assign statement, the same output will retain 0. Here sometime it is 1. After that it is 0. Up to here it is 0. See, this is 0. No. And then it is becoming 1 and it is holding the value. So this is with assign. So now what you understand, assign means continuous assignment of variables in the right side to the left side. Okay, the operation also will perform B and C. So it means even though B and C are not changed from the user, from the outside, still the B and C operation is performing and that assignment is happening. So that is what we can, that's why it is called as assignment, continuous assignment. And here also all the arithmetic operators are valid. A plus B plus minus multiplication. This is for a quotient and this is for remainder. Same how we are using in C. And for multiplication, I think 2 stars, not 1 star. Sorry, 1 star means multiplication. And if you want to write some A power B, then you have to give A double star B. This is the only extra thing which you are getting in the wet block. A power B also positive with a double star. In C, we are using A power B, right? But here the cap we are using for XOR operation. So that's why we are using 2 stars. And the remaining operators also valid, like A less than B. These all you might have heard. If A less than B, some code you can write begin end. If A less than equal to B, these all you can use normal coding language C or anywhere you can find it. A while A less than or equal to B, you can execute begin and end. But don't forget to write begin and end in the inside the loop. These are all the normal operands. There is nothing special in it. And equality operators, right? Equal to if A equal to B. So that means it will execute this code if A and B are equal. But remember, this equal only works if both are valid values, zeros and ones. Okay, if any one of them becomes X or Z, then this will not valid. Even though both are become Z, then still it will become false. Okay, this double equal to only works if the inputs are 0 and 1. If you have the in any one of the input is having Z or X, then you have to give 3 equals. So then it will compare along with 0, 1, X, Z also. All the values it will compare. Okay, and not equal to all you might have not equal to. Okay, same thing. Same thing, if you add one extra equal to, then it will consider X and Z. If you add only one equal to, then without X comma Z. And there are some logical operators as well, which you can use inside if statement. A and B. So this is, we can say, 2 statements. If you give, this is one statement, and this, let's say if I write if A is equal to B and C equal to D. This is the way you can use logical AND. It means this is logical AND. So whatever the statement which is present on the left side and the right side, both should give the same value. If this is true, then only this entire AND will give a 1. If any one of them becomes 0, then it will perform AND operation between 1 and 0. Okay, we can say it is a simple logical AND. Okay, not with a digital binary AND. Okay. Same way you can use 2 ORs, logical OR. If any one of the statement is true, then it is true. You can use the variables also. Here, if I can use A and B also. So then what will happen? It is considering the values of A and B in terms of zeros and ones. Always is, whenever the specific condition which you written in the always block is true, then only it will enter into always block and it will execute. But assign is a continuous assignment. Even though there is no change in the value of B and C, anything, it will keep on executing the assign statement from the start and end of the simulation. Okay, from the start of the code, if you are executing from the start to end, the assign statement is keep on assigning the values irrespective of the condition. But the always block has some condition. See, always at the rate, you are writing some condition. If you remove always, if you write always at the rate, here you give star, then it is equivalent to assign statement. Whatever the value, it will still keep on executing from start and end of the run. Okay, but always block is used to write some condition usually. Okay, so here it will check if you give an and right, it will check whether 1 or 0, both the values. Okay, if it is 1, then it will execute, it will give 1. So both are 1 and 0, it will give 0. So if you are given both of them 1, then it will give 1, then its block will be true and it will going into inside this block. No, you given condition, right? A, B, C. It means if any change occurs in A, B, C, then only it will enter into the always block. But here essence statement, even though there is no change in B and C, A is keep on assigning, keep on updating with the values. So it can hold the values. But in the above case, even if there is any change, A, B, and C. But if you declare A as a register, then output you are getting in both the cases it is same. If you declare A as a wire, then there will be a difference. But the definition point of view, how you have to understand, if you write always block something you have written, right? If there is any change happens, A, B, or C, any one of the variables got changed, then always block is executed. Okay. And okay. And here you need to understand some logical way in this very law because it is replication of digital funds, right? So few operations you have to understand in logical way. So let's say I'll try to give more details on bitwise AND. Let's say I write A equal to B and C. It means it will do bitwise AND operation. If you see one AND gate, one AND symbol, then you can blindly think that it is an AND gate in a digital fund. So, but how the AND gate will perform, it will take only 2 bits. So, but if these are single bit, all are single bits, then it is a simple AND. A, C, sorry, B, C, it is A, that's it. But if input I can write 3:0, B comma C, and output I can write 3:0, okay, then what it will do, if you write this code, then it means A of 0 equal to P of 0 and C of 0. A of 1 equal to B of 1 and C of 1 until A of 3. Same thing happens. Even if you write with assign statement also, that is assign. So try to remember, if you declare anything wire input or output, then try to use assign statement except registers. For registers, you can use normal SNA. So for this, so from this point onwards, remember the good code is try to use assign statement instead of direct A equal to B equal to C. Okay, because if you use assign, then you need not to check whether it is declared as a wire, register, input to output, whatever. Okay, so that's why always try to use assign statements. Assign A is equal to B and C. Let's say this is the code. And these are 3 bits. So it means it is bitwise AND. That's why we can call it as a bitwise AND. If I give same thing, assign A is equal to B and C. Let's say for time being, these are 1 bit, single bits. If B and C are single bits, then single and double AND both will give same output, same result, we can say. Okay, if B and C are, if B comma C are single bit, understood? But if B and C are different, are like 3 bit or 4 bit input, then the above one will do bitwise AND. But here what it will do, it will consider B, entire B bits 1 1 1 and 1 1 1. Only in this case, this second statement is giving 1. For all remaining, it will give 0. Okay, here it will give only 1 bit output, even though inputs are 4 bits or 3 bits. Output is always 1 bit in the second condition if you use double AND. Okay, so irrespective of the number of bits in the input, output is always 1 bit, either 1 or 0. But here in the above case, if it is 4 bits, then it will deliver you the 4-bit output. That's why we can call it as a bitwise. Here it is logical OR. Okay, that is the difference you need to understand. Logical OR in the sense, if you give B 1010, logically it means B is not equal to 1. It is considering like this. Okay, that is what the difference between normal AND and logical AND. You need not to go deep in this Verilog. Just if you understand something written in the Verilog file, if you understand good, then it's fine. And shift operators also, shift operations, you know, right? Shift by left, shift right. Same symbols we can give, right? This double arrow. You give, it is a shift operator. If you give single, it is greater than, it is less than. So if you give this one, it means shift right, shift to right. If I say logical shift operands, arithmetic shift operands. Okay, let's find the difference. Let's say my input A is input 3:0. Okay. So this is my input, and my output is 3:0 of B. Okay, but B equal to A right shift by 2. If I given two symbols, shift symbols, then it is logical shift operation. Okay, so it means if I give my value of A, let's say is 1010. So I'm right shifting by 2. What is the number is 2? So it should shift 2 times. Okay, 2 times means, so this one is shifted here, this 0 is shifted here, this one is shifted here, this one shift, and I send 0 here, and the next shift means this 0 is shifted here, this one is shifted here, this 0 shift here, this 0. This is the shift operation we perform. Logical shift we can say. Okay, let's find out difference between. So if I give A greater than 3 symbols, then we can say arithmetic shift. Okay, so let's try to find the difference between logical shifting and arithmetical shifting in a Verilog. Guys, 1 second. It's like we'll continue till 12:30 because I want to cover this very long today. 12:30. Just give 1 minute. I have to change this microphone. The charging is low. One and then one and then zero. So this is what happened. What is the difference between arithmetic and logic?
Hello.
If you're giving unsigned number, Both will perform
Yeah,
same.
that
If you
noise
give
some
sign
other
number,
class
then there will be a
is
difference.
coming into my class, like some.
If you give
good
negative numbers,
connection
we can
is
say.
working with my-
If you're giving positive numbers, still 1, 0, 1, 1, 1, if I want to shift, so that doesn't matter, right? 0
Ah,
here,
side it is
0.
connecting well.
1, 1.
Yeah.
And if it arithmetic shift or
should-
logical
it should
shift,
blink
still it is giving 0,
For connection, correct?
0 and 1. That's it.
Okay, it should not blink. Yeah.
Okay, these are some operators.
Yeah. Okay, let me try. This is. Yeah, receiver is still blinking. I try turn off and switch off. Yes. Okay. Okay.
Oh.
You have to talk, but
Otherwise,
still it is
hearing other person.
blinking only.
Okay, then fine. Anyhow, it's all right. Okay, we'll continue.
Might
in the
get
next class.
connected with some other device.
I don't think it will resolve because till now I connected my Bluetooth earphones, but now the charging also very less. Even if I use my Bluetooth, you cannot hear. So it's like other class started. Okay, we'll close today's class. We'll continue the Verilog in the next class. Next Saturday, we'll continue. Okay, mostly I'll take from my home, so I'll cover with my own laptop. Okay, because it's Verilog, and I'll try to start Unix as well. Otherwise, we'll discuss in other classes. So I'll try to complete this Verilog and Unix by the end of this month. I think May 28th or 29th. By that weekend we'll complete this Verilog and Unix, all of them. And from June first week we'll start DFT.
Sir, for PD people, it is common for these topics.
Till Unix it is common.
Common.
Till Verilog and Unix it is common. From June first week, then you probably they will assign you the other class.
Okay.
Okay, from I think by end of this month you can continue in this class. After that, I think a new batch started, I guess. I'm not sure. The syllabus they'll assign you in that class.
Okay.
Okay. So in the next class, we'll take one question and we'll try to write the Verilog code in 3 modelings. Okay, and then we'll close the Verilog in the next class.